Flicked her back there. Hello everybody. In today's session, I am continuing with the transformers. Today's session we see this EMF equation. Now the slide what I opened today, it is this EMF equation. Normally for a transformer it is connected in the AC supply systems, where I will be giving a sinusoidal voltage of V1 to the primary, and this winding will draw a current from the supply and produces a sinusoidally varying magnetic field or magnetic flux in the core. This flux can be represented by an equation phi of t is equal to phi m sin omega t, and this omega will depends on the supply frequency of f hertz. So replacing omega by 2 pi f, I will be getting an equation for the flux as phi m sin 2 pi f t. The supply frequency and the frequency with which this magnetic flux alternates will be the same. Now with this flux have a maximum value of phi m or the peak value of phi m, and the frequency as I mentioned here will be equal to the supply frequency. Therefore we can say that the magnetic flux produced by the primary winding in the core is alternating, okay, in nature, and it is following a sinusoidal curve. Now the induced EMF in the primary winding of T1 turns, it is given by this expression, E1 is equals to minus T1 d phi by dt. Okay. Now the flux what is produced by the primary winding will also links with the primary winding. So as the flux is alternating, there will be change in the magnitude of the flux. So as per the Faraday's laws of magnetic induction, whenever there is a change in the magnetic flux linking the primary winding or any winding, in fact there will be a voltage induced. Now this induced voltage will have a direction according to Lenz's law. Now this law says the EMF, okay, which is induced will oppose the very cause of production. Now the cause of production for this induced voltage in the primary winding is alternating flux, okay. So because of this I will have a minus sign for this equation, E1 is equals to minus T1 d phi by dt. This d phi by dt, okay, d phi by dt will give you rate of change of flux linkages, time rate of change of flux linkages. The flux which has a value of phi of t is linking with the primary winding of T1 turns, therefore there will be flux linkages of phi T1. Now because the flux is changing, the flux linkages also changes. This change in the flux linkages will give you a voltage, so that can be represented by T1 d phi by dt, and the minus sign is because of the direction, okay, direction of the induced voltage you can say. Now by replacing the phi with this equation phi m sin omega t in this expression for the EMF, I will be getting t minus T1 d times phi m sin omega t by dt. So this is rate of change of flux, okay, in which phi m is constant, the maximum value. Therefore I have to differentiate the sin omega t with respect to t. So that gives us minus cos omega t. Therefore I will be getting here T1 omega phi m cos omega t, right. Now when I substitute for this omega a 2 pi f, I can also do that. Otherwise you can simply write down that the product what I have here, T1 omega phi m, will give you the maximum value of the voltage induced in the primary winding. I should have written here EM1, okay, representing the primary. Fine, no problem here. So the maximum value is given by T1 omega phi m. So in case of AC circuits, we have the RMS value of the voltage will be maximum value by root 2. Therefore I can substitute EM value of T1 omega phi m with omega is equal to 2 pi f. So, I will be getting here 2 pi f T1 phi m divided by square root of 2, that comes to be 4.44 f T1 phi m. Okay. We can also there are several methods of deriving this EMF equation. This is one of the simplest methods, therefore, I just prefer to give this method. Now, the flux which is produced by the primary winding after linking with the primary, it passes to the core, magnetic core. Okay. So, the core, after passing to the core, the same flux which is linking with the primary also links with the secondary winding. Okay. Now, the secondary winding has T2 turns. So, there will be flux linkages in the secondary winding, which is given by the product of T2 phi, okay, where phi will be phi m sin omega t. So, because the flux is sinusoidally changing with respect to time, there will be change in the flux linkages in the secondary also. So, that change in the flux linkages will give you an EMF induced in the secondary winding. Okay. So, that EMF induced will have an RMS value of E2 is equals to 4.44 f T2 phi m. Okay. Now, if I just take this E1 equation, that is the RMS value of the voltage induced in the primary, and see, you can just remember that the equation E1 is equals to 4.44 f T1 by phi m. Okay. The primary has T1 turns, induced voltage has an RMS value of E1. So, if I divide E1 with T1, I will be getting the voltage per one turn, that is the voltage induced in one turn of the primary winding. Same lines, if you see this EMF equation E2, we also have an expression here, E2 is equals to 4.44 f T2 phi m. Again, when I divide E2, the RMS value with T2, I will be getting the voltage induced in one turn of the secondary winding. So, that is called as volt per turn. So, it is E2 by T2 in the secondary and E1 by T1 in the primary. So, both equations here, E2 by T2 and E1 by T1 will have the same expression as 4.44 f phi m, which means that both the primary and secondary winding will have same amount of voltage induced per turn. Because the number of turns are different, I will be getting a different amount of voltage in the primary as well as secondary winding. So, this says the volt per turn is constant for a given transformer. Now, for every transformer there will be a ratio called transformation ratio, which tells about how the voltage is transferred, okay, by what magnitude the voltage is transferred from primary to secondary. Okay. We normally write this as the ratio of secondary voltage to primary voltage. It is called the transformation ratio or turns ratio also. This is represented by letter K, okay, capital letter we will use. So, the RMS value of the induced EMF E1 is 4.44 f T1 by T1 phi m, and for secondary E2 is equals to 4.44 f T2 phi m. When I try to write down the ratio K is equals to E2 by E1, because this 4.44 f phi m is common for both the equations, I will be getting E2 by E1 is equal to T2 by T1. Okay. So, that is transformation ratio is equals to the turns ratio. Okay. Voltage ratio V2 by E2 by E1 is equals to T2 by T1. I have taken this as induced voltage in the secondary to the induced voltage in the primary. I can also write down this ratio in terms of voltage at terminal voltage of the secondary V2 and the voltage applied to the primary E1 V1. So, V2 by V1 is equals to T2 by T1 also we can write. Okay. Now, if the transformation ratio, this K is greater than 1, you can see here when K is greater than 1, our E2 will be larger than E1. Therefore, I call the transformer as step up transformer. Okay. Generally, the step up transformer is used at the generating station, okay, at the generating station for stepping up the voltage generated from 11 kV to a transmission level of 33, 66, 110, whatever levels we use for the transmission. Okay. So, that level we can step up. Now, if the transformation ratio K is less than 1, I call the transformer as step down. Okay. I am sorry, here both are written as step up, this should be step down. Okay. While copying and pasting here I did a mistake, this should be a step down transformer, because K is less than 1, my secondary voltage will be lesser than the primary voltage. Such kind of transformers we will be using at the receiving end, okay, where the voltage of transmission from 440 or 230 or from 33 or whatever transmission voltage level is there, from there it will be stepped down to distribution level. Therefore, I call the transformer as step down transformer. This is not step up, step down it should be. Okay. Now, it is also possible to use a transformer with a transformation ratio of K is equal to 1, which means both the primary induced voltage and the secondary induced voltage, they are equal. That means the primary winding and secondary winding will have equal number of turns. Okay. Such transformers we call them as isolation transformers, which are used in electronic circuits, where I want to maintain two circuits at the same voltage level but without any electrical connection. Okay. Such transformers we call them as isolation transformers or 1:1 transformers. There is no step up or step down, both are equal. Okay. Primary voltage and secondary voltage are equal. Therefore, there will be electrical isolation between the two, as there is no electrical contact between primary and secondary circuit in the case of transformer. Okay. So, therefore, I call the transformer as 1:1 transformers. Okay. So, every transformer or every electrical device should have losses, because it is not possible to get the same amount of output input as output. Okay. Now, here what we are doing using a transformer is, I am converting the electrical power from one voltage level to other voltage level. Both input as well as output are electrical in nature, but it is not possible to get the same amount of input what I am giving to the transformer at the output. Okay. So, in a transformer, the loss can be defined as the difference between the input power and the output power. Now, the transformer will not have any rotating devices. Okay. Therefore, I call the transformer as a static device. So, as the rotating parts are absent, we can say the mechanical losses, which usually gives us windage and friction losses, are absent. Okay. The losses in a transformer, actually we have only two types of losses here: iron losses, okay, which takes place in the core of the transformer, and the copper losses, which takes place in the windings, primary and secondary windings. Okay. The iron loss has two components. One is called hysteresis loss, and second one is the eddy current loss. Eddy current loss and hysteresis loss depends upon the magnetic properties of the materials used for the construction of the core. Okay. Depending on the material we use, we have the value of these losses, okay, like that. So, now actually normally when we are designing the core of the transformer, we always select a suitable material for the core, so that these losses are minimum. Particularly hysteresis loss will be minimized by selecting the suitable material, okay, which has low amount of hysteresis loss or the narrow hysteresis loop. Okay. Now, since these losses are taking place in the core, I can also call this as core losses, because the core is made up of iron. I call it as iron losses. So, out of these two losses, iron loss and hysteresis loss, it is not possible to avoid any one of the losses. Okay. Hysteresis loss will be there, and eddy current losses also will be there. Now, this hysteresis loss, it is due to the reversals of magnetization in the transformer core. Now, see, this reversals of magnetization is a must for us, otherwise there won't be any energy transfer from primary to secondary. Now, because of this reversals of magnetism only, I am getting a voltage induced in the secondary winding when I connect the primary to the supply. Okay. So, therefore, if you want to get an output for the transformer, there should be a induced voltage in the secondary. Unless there is a reversals of magnetism in the core, you can't get the voltage induced in the secondary. Therefore, this reversals of magnetism is very important in the transformer. So, therefore, whenever you have this reversals of magnetization, there will be hysteresis loss, because the core is continuously subjected to reversals of magnetism. So, that core will definitely show a property called hysteresis. Only thing is, to minimize the loss, I need to select a suitable material which has a narrow hysteresis loop, which means the energy wasted during the flux reversals in the magnetic core will be minimum. Okay. So, this loss depends upon the volume and grade of the iron. Okay, so that grade means whether it is ferromagnetic, magnetic, or like that type of thing. Okay, property. Frequency of the magnetic reversals and value of the flux density. Now out of this, the volume is constant. Okay, the volume, because once I construct the core, I will not be going to change that core, therefore volume is constant. The material also I will not be changing, so for the grade of the iron is also constant. Now the frequency of the magnetic reversals, this is proportional to the supply frequency. Now we maintain a frequency of 50 Hz in our country, therefore this frequency of magnetic reversals is also constant. Okay, and the value of the flux density depends upon the magnitude of the voltage what I will be giving to the transformer. Okay, therefore now since the primary supply voltage is also a constant, all the 4 parameters what you have here, volume, grade, frequency of reversals and the value of the flux density, all are constants, therefore this hysteresis loss is a constant loss. Okay, now this hysteresis loss is given by a formula called Steinmetz formula, where WH, H stands for hysteresis, is eta. Okay, this is not efficiencies. Okay, it is a symbol, it is only. Okay, normally efficiency will be presented by this sign, symbol eta, but here it is only a constant called as a Steinmetz hysteresis constant. Okay, then the maximum value, okay, B max is the maximum value of the flux density raised to the power of 1.6. Okay, supply frequency F, V is the volume of the core in meter cube. So as all the 4 parameters are constant here, I can say the hysteresis loss is constant. Okay, so only way to minimize this hysteresis loss is to select a suitable material which has very narrow hysteresis loop. It is not possible to avoid this hysteresis loss in the case of transformers. We can only minimize them. The next loss what is taking place in the core is the eddy current loss. Okay, now this eddy current, it is an induced current. Okay, in a transformer, AC current supplied to the primary winding sets up the alternating flux. This flux also links with the conducting part. Okay, the copper windings are what I called as a primary winding, that is a conducting part, right, and the steel core what we are using, that is also conducting, but I am not directly giving any current to the core. The core will carry only the magnetic flux which is sinusoidally alternating. Okay, this flux which is moving through the steel core and reversing in direction, okay, at a frequency of F, is responsible for the induced EMF in the core. Now this induced EMF causes a circulating current. Now this circulating current will be opposed by the resistance of the core, which is inversely proportional to the cross sectional area of the core. Okay, now this induced EMF what you have, it will not contribute towards the energy transfer from primary to secondary of the transformer. Okay, therefore this energy is just wasted in producing or developing a heat. Okay, so because of that heat developed, the temperature of the core will increase. So if the temperatures continuously increases and goes beyond a limit, then the magnetic properties of the core will change. Okay, so because of that I need to minimize this eddy current losses. Now this current induced in the core is called as eddy current. Okay, this is just a loss, it produces only loss. Due to these eddy currents, some energy will be dissipated in the form of the heat in the core. So that heat is called as eddy current loss. Like we also have a formula here to calculate the eddy current loss. Okay, different textbooks will give us a different formula. So this is one of the standard textbook what I have taken here. Okay, this formula is from a standard book. See, E stands for eddy current. So WE is the eddy current loss, okay, which is measured always in watts. KE, it is called as eddy current loss constant. Bmax is the maximum value of the flux density. Okay, Bmax is the maximum value of the flux density raised to the power 2. Okay, Bmax square, F square, V, T square. Okay, this T square what you have is T, what you have is the thickness of the volume, thickness of the lamination. Okay, now here also this eddy current loss is a constant. The transformer flux, maximum value of the flux density here depends on the maximum value of the flux okay, and it inversely proportional to cross sectional area of the core, fine. F is the frequency of reversals, V is the volume of the core, T is the thickness of the core, okay. So as we have here all constant terms, this eddy current loss is also a constant. So out of these two losses, hysteresis and eddy current losses combined together, what we call it as core loss, will be a constant loss in the transformer, okay. So eddy current losses within a transformer core cannot be eliminated completely, but we can greatly reduce and control the reducing the thickness of the steel core, okay. Instead of having one big solid iron core as the magnetic core material of the transformer, okay, or coil, the magnetic path is split up into many thin pressed steel shapes called laminations, okay. I have shown you in the yesterday's session the different types of laminations what we use. All those laminations will have a thickness of somewhere around 0.35 mm, okay. Now see here, I just shown a small diagram in this. When you use a solid core, okay, hope you can see a mesh type structure in this core. So this is the cross section of the core. Now the flux lines, what you see, what you have in this core will be moving perpendicular to this core area, okay. That means they will be going inside or coming out at 90 degrees to the rectangular face. Therefore this complete area will be offered for the eddy currents induced in the core, okay. As you can see, the area is larger, okay. Resistance offered by the core will be smaller because the resistance is inversely proportional to the area, okay. Rho L by A, it is inversely proportional to area. Therefore I will be getting a smaller area offered, sorry, larger area offered by the core to the induced EMF in the core because of the flux reversals. Because of that, I will have a low resistance offered. So that low resistance causes a large amount of eddy currents flow through the core. Now if the same core with the same dimension, if I can laminate this, okay, like this is the lamination. See, I am showing the rectangle area what you have here made up of 1, 2, 3, 4, 5 laminations, okay. Now the thickness of the lamination will be smaller compared to this rectangular thickness what you have here cross section. Therefore the area offered will be only the area of one lamination, the thickness, okay, rectangular area of one lamination. Now you can see a thick line between two lamination. So this is a insulation, okay. So now because of this insulation, a varnish coating, usually there is the currents what is induced in this lamination cannot go to the next lamination because of the insulation what you have here. Therefore the area offered by the core to the induced EMF due to flux reversals within the lamination is restricted to a smaller size. Because this area is reduced, okay, the resistance offered will be larger compared to this. Therefore the eddy current what you have in this lamination will be much smaller compared to the induced current what you have in this bigger rectangular core. So this is how I can minimize the magnitude of eddy current losses induced in the core of the transformer. Thereby I can also minimize the temperature rise of the transformer, okay. So the result of all this insulation what you are providing between lamination, okay, it is to reduce the eddy current power loss, okay. It will be reduced to a great extent. So using lamination in a transformer construction reduces the eddy current losses. So finally the core loss I can minimize, okay. One component of the core loss, which is hysteresis loss, that can be minimized by minimizing the amount of energy wasted during the flux reversals. For that I need to select a material for the core which has lesser or narrow hysteresis loop, okay. Whereas for minimizing the eddy current loss I need to laminate the core. So these are the two methods by which we can minimize the constant losses in the case of transformers. All transformer cores are made up of such type of construction. Therefore the transformers will have very small amount of core losses and which are always constant and independent of load what we call. The second loss in a transformer, this is the major loss, what we call it as a copper loss. Now generally we use copper for the winding, okay. Therefore, I call the loss as a copper loss. It does not mean that if I use aluminum as a conductor for the transformer, I can call the losses as a aluminum losses, okay. But still, because generally we used to use this copper in olden days, now as the copper is costlier, I can use aluminum also as the material for the conductor, but these losses we still call them as copper loss or I square R loss, okay. And this is due to the electrical resistance offered by the primary and secondary windings to the flow of current, okay. Now this resistance opposes the magnetic currents flowing through them, okay. Of course, this is just basically the series resistance of the coil what you have in the transformer winding. So when a load is connected to the transformer secondary winding, large electrical currents flow in both primary and secondary windings, okay. Say like this, I have a transformer, so this is the core of the transformer, I am just showing a core type. So whatever the type of the transformer we are using, this explanation holds good even for that. This is the primary winding of the transformer, this side I have a secondary winding. I am connecting a supply to the primary with a voltage of V1 at a frequency of F. Now this will set up a flux of 5 Webers in the core. That flux links with the secondary winding, of course it also links with the primary, gives us a voltage of E1 induced in it, and the same flux will induce a voltage of E2 in the secondary, with primary having T1 turns, secondary having T2 turns. Now when I connect some load across the terminals, okay, the voltage what is available at the terminals is V2, what we called as normally secondary terminal voltage, and E2 is the secondary induced EMF, E1 is the primary induced EMF, V1 is the supply voltage. There won't be any change in the frequency, so all the voltages will have the same frequency of F. Now when you connect a load here, the induced voltage what you have here will allow a current to flow through the secondary winding. Now this current will be given to the load at a voltage of V2, okay. What is happening between E2 and V2 means, because this winding has a resistance, okay, and it also has an inductance because of the change in the flux reversals, okay. Now this inductance what you call for the secondary winding, it is because of the leakage flux linkages, okay. Let us not bother about that, we just consider that the secondary winding has a resistance of R2 and an inductance of L2 Henry, which gives us leakage reactance of X2. The combination of these two, when it will carry a current of I2, a small amount of voltage drop will be there. So from E2, if I subtract that voltage drop, I will be getting this V2, okay. Now when the load is not there, there is no current in the secondary. Such case, the primary will draw a smaller amount of current sufficient to produce the flux in the core. The moment you connect a load onto the secondary winding, the secondary will give us a current I2, therefore the primary along with the current what it is drawing to produce a flux Phi2 draws an additional current, okay. Let us call that current as I1. Now see, when the transformer is under no load condition, the secondary is not carrying any current, but the resistance is still there for the secondary, therefore the copper loss is not there in the secondary winding. Whereas under load condition, because the current is considerable magnitude, there will be a copper loss or I square R loss in the secondary. Then okay, under this condition, because the primary is drawing an additional current to supply the load, there will be a resistance of R1 for the primary, therefore I have I1 square R1 as the copper loss or I square loss in the primary winding. So I have the transformer with two windings carrying different currents, right? Both windings will have copper loss or I square R loss, I1 square R1 in the primary winding, I2 square R2 in the secondary winding. Add up these two, I will be getting the total copper loss or total I square R loss in the transformer. Okay. Now, because the copper loss are also called as I square R loss, this I, the current what you have in the secondary I2, it depends upon the load. Okay. As you keep on increase the load, I2 also changes, therefore I call this I2 square R, R2, that is the copper loss in the secondary, a variable loss. Similarly, the copper loss in the primary winding I1 square R1, that is also a variable loss. So combined together, I will be getting the copper loss as a variable loss. Okay. So in this slide, I just gave you about the core losses again. See, core loss for a given transformer depends on the supply voltage, as the frequency and other parameters are constant. Okay. And of course, the supply voltage is also constant, therefore the core loss are constants. Hysteresis loss can be minimized by selecting suitable core material. Laminating the core reduces the eddy current loss. Okay. For all given transformer, under all load conditions, the supply voltage and the frequency of reversal flux are constant. Okay. Therefore, the core loss are constant. This I repeated many times. Okay. And for the transformer, you can see the primary current and secondary current are also related through the transformation ratio. When the secondary current changes, the primary current also changes. As load on the transformer is varying, the copper losses will also vary because the currents in the primary and secondary winding changes. Okay. Just now what I told you about that copper loss, variable loss, these statements will support that. Then coming to the efficiency of the transformer, I can always calculate the efficiency by dividing the output of the transformer to the input with the input. Okay. Output divided by input is the efficiency for a transformer. This is called as power efficiency for the transformer, wherein this output and input will be expressed in terms of watts. Okay. Transformer are most highly efficient, okay, electrical devices. Now generally the transformer will have an efficiency between 95 to 98.5%. Okay. Now that the reason for this is the losses in the transformer are only two, that is core loss and the copper loss. There are no rotational losses, so therefore the output of the transformer will be very close to the input, therefore I will be getting a larger amount of efficiency. Okay. Now a better method to find out the efficiency of the transformer is using the equation like this: efficiency is equals to input minus losses by input. Fine. So I can just measure the losses in the transformer by conducting some suitable tests, and for a given rating of the transformer I will have the efficiency given by this equation. Remember, in the transformer the two losses what you have, core loss, they depends on the voltage, okay, and the copper loss or the I square R loss, they depends on the current. So the product of voltage and current will be volt amperes, therefore the rating of the transformer will be always expressed in volt amperes. Okay, that is the product of voltage and current. If the transformer has a primary winding rated to 230 volts and the current is somewhere around 4.7 amperes, okay, or 4 amperes, let us say, for simply case I will take 250 and 4. 250 is the voltage in the primary V1, 4 amperes is the current in the primary I1. So 250 multiplied by 4 will give you 1000 volt amperes. This will be the rating of the transformer. Okay. Fine. If I take a 1:1 transformer where the secondary also have 250 volts and the current of 4 amperes, then the secondary is also rated to 1000 volt amperes. Okay. This is the product of V2 I2. Actually this I1, it is the current in the primary, I2 is the current in the secondary. Okay. Now when the load is not there on the transformer, there will be a small current taken by the primary winding I0 sufficient to produce the magnetic flux in the core. A small portion of this will be represented by current IL, which is responsible for production of core losses. Okay. So therefore, under load condition, the primary current I1 will be equals to I0 plus the secondary current measured from the primary side, or it is equivalent to secondary current, what we call. Okay. When I neglect this, which is very smaller compared to this, okay, when I neglect this, I can take the I1 to be equal to I2 dash. Therefore, the product what you have V1 I1 is equals to V2 I2 for a transformer. Okay. That means primary volt amperes is equal to secondary volt amperes for the transformer. Yesterday we saw that the transformation ratio is given by E2 upon E1. Okay. This is also can be written as V2 upon V1. This is equals to I1 upon I2. This is how the voltages and currents in the transformer are related to the transformation ratio. When you read this equation, what I highlighted here, you should consider E2 to be the induced EMF in the secondary, E1 to be the induced EMF in the primary, V2 is the secondary terminal voltage, okay, V1 is the primary supply voltage, I1 is the primary current, I2 is the secondary current. Fine. For a transformer, always the primary volt amperes is equal to secondary volt amperes. So if you see this slide, I can just measure the losses in a transformer, okay, and use this equation to calculate the efficiency of the transformer. See, as the core loss depends on the voltage and the copper loss depends on the current, the transformer power rating will be in volt amperes. Okay. The output and input are measured in volt amperes for a transformer. The losses are measured in watt. Therefore, in the expression for power, the input what you have should be always in terms of watt. Okay. I can't substitute volt amperes there. Therefore, I need to consider the power factor of the load in calculating the efficiency of the transformer. Okay. So, secondary voltage, secondary current, and the cosine of the angle between voltage and current, that will give you the output of the transformer or the volt ampere rate, the power rating of the transformer from the secondary in terms of wattage, okay, watts. If this cosine term of the angle is not there, the product I will get in volt amperes. Because of this cosine of the angle between voltage and current, I will be getting the transformer output in terms of watt. Okay. See, for a full load output of a transformer is V2 I2 cos phi 2. Cos phi 2 is the angle between V2 and I2. Okay. Core loss is Wi. Full load copper loss is WCU. Therefore, full load efficiency we can calculate like this: output divided by output plus the total losses in the transformer. At any load other than full load, output of the transformer, okay, output of the transformer will vary. What do you mean by that? Transformer is supplying a load at a voltage of V2, but the current I2 is not the rated one, it is lesser than the rated one. Okay. Other than full load means load, any other load other than full load. That load can be lesser than full load or greater than full load. Normally we do not load the transformers above the full load value. Therefore, I will be considering load other than full load means it is a fraction of a full load. Okay. That means less than full load. Okay. The transformer output will vary, copper loss will vary, iron loss will remain constants. In this equation, I just given it as a full load efficiency, where V2 is the rated value, I2 is also the maximum current what is allowed as per the rating of the transformer. Okay. If I just take the rating of the transformer, divide that rating with the voltage on the primary or the secondary side, I will be getting the rated current. Let us, I told you here, 1000 volt amperes is the rating of the transformer and the winding is rated to 250 volts. So 1000 divided by 250 will give you 4 amperes. So this is the full load current for the transformer. Any current less than full load 4 will be reduced current, okay, reduced load we can call that. Okay. Here I just mentioned here for a load factor X, I just defined the X as a secondary current of any load divided by secondary current at any load divided by full load current, right. Suppose say my secondary rated current is, the full load current is 10 amperes, I am just taking only 5 amperes to the current secondary, then 5 divided by 10, how much I get? 0.5. That means the transformer, instead of giving 10 amperes, okay, it is giving only 5 amperes, 5 is half of the 10, therefore I can call the transformer as half full load. The load on the transformer is half the full load, okay. So the output at this load factor will be x V2 I2 cos phi 2, okay. V2 remains the rated value, the current is decreased by x times, okay. So core loss is Vi, copper loss is x square times Cu, WCU, okay, because copper loss varies with the square of the current, okay, that is why I will get x square. I reduced by 0.5, okay, so I square R, so 10 amperes will give you 10 square 100, whereas 5 amperes will give you 5 square 25, so 25 divided by 100 is 0.25, right. So when the current decreases by half, okay, the copper loss decreases by 1/4 times, that 1/4 is 1/2 whole square I can write. So when x becomes 1/2, copper losses becomes 1/2 square times the full load copper loss, okay. Efficiency at any load x can be calculated by using the output at any load divided by output at any load plus iron loss plus copper loss at that load, okay. I just mentioned here, if the full load current is 25 amperes and the transformer is supplying 15 amperes to the load, then the load factor x will be 15 divided by 25.6, okay. For any transformer x can vary between 0 to 1, okay, 0 for no load and 1 for full load. Usually for any transformer, the design of the transformer is such that it is possible for us to load the transformer slightly above the full load, not for a long time but for a specified time, okay. So therefore x sometimes can also have a value of 1.25 or 1.1 like that, above value of 1. Anything above 1 x, it is overloaded, okay. So I have, when you have a efficiency, somewhere at one load the efficiency should be maximum, okay. So efficiency can be computed from a primary side also, like in the previous slide what equation I have given for the efficiency, it is with respect to the output. Now instead of calling the efficiency as input output divided by output plus losses, I can also write down the efficiency as, see, efficiency is usually we write like this, output divided by output plus losses. Instead of writing like this, I can also write it as input minus losses divided by input. This also will give us the efficiency, okay. What is the difference is, here I am following the secondary, from the secondary side I am calculating the efficiency, here I will be calculating the efficiency from the input side, okay. Now whether you calculate the losses either from the output side or from the input side, there won't be any difference, the losses are same, okay, losses will remain same. So when I can also use this equation, input minus losses by input. So in explaining the condition for maximum efficiency, I will be using the second equation in place of this first one, okay. I just, if you see the slide here, here I mentioned efficiency as input minus total losses divided by input. So as I am measuring the input, I should consider the primary voltage, primary current and the angle between the primary voltage and primary current. Remember, when you calculate the output efficiency and the input and all, I will be using only the RMS values, okay. V1 is the RMS value of the voltage on the primary side, I1 is the RMS value of the current on the primary side. Core losses are Wi, copper losses also WCU, okay. So this efficiency can be written as input minus losses divided by input. I will just expand this equation 1 minus Wi divided by V1 I1 cos phi 1 minus WCU, okay, that is written as I1 square R equivalent 1, okay, divided by V1 I1 cos phi 1. Now this relationship what I have used here for WCU as I1 square R equivalent will tell us that the copper losses are measured from the primary side, okay. Therefore, I have written the expression as I1 square. Now this R equivalent 1, it is the equivalent combination of the secondary resistance and the primary resistance measured from the primary side, okay. Let us not bother about what is the equation for this and all, but simply you can see when I measure the copper loss from the primary side, I will be using this equation. If I measure it from the secondary side, then I write it as I2 square, okay, I2 square secondary current R equivalent to 2, I write that, okay. There is a simple relationship between the transformation ratio K, primary resistance R1 and the secondary resistance R2 to write down this equation, okay. Now that equation is not necessary for our subject point of view, therefore you can just simply remember this, okay. WCU when measured from the primary side will give you is given by this equation I1 square R equivalent 1. That means to get this equation, about this equation what you have, each term of the numerator is divided by the denominator term, okay. Now in this equation V1 is the primary voltage, that is a constant one, iron loss is also constant. So when the load varies, the current I1 will vary here, I1, okay. This is the only variable what you have in this equation. Phi 1 and all, it depends upon the type of the load what is connected, okay. Normally the transformer is an inductive device, always the current I1 will be lagging behind the voltage by an angle of phi 1, okay. So that current I1 is the variable in this equation. I want to have a maximum efficiency, so if I go for maxima and minima condition, I need to differentiate the current equation, sorry, efficiency equation with respect to current, okay. Here it is written as T in this, but it is not T, it should be I, okay. This should be I, D efficiency by Di, because the variable is I there, okay, should be equal to 0. So on differentiating this with respect to the current, okay, I have, if you see the previous equation, I have I1 in the denominator of the second term. Therefore remaining terms being constant, I need to differentiate 1 by I1, right. Here I can cancel one I1 with this, one I1 in the denominator. So I1 square divided by I1 will give results in I1 only, okay. So if I differentiate the two terms, the first term will give you minus 1 divided by I1 square, okay. Second term is differential of I1 is 1. By simplifying this equation, I will be getting a condition that I1 square R equivalent 1 should be equal to Wi. What is this I1 square R equivalent 1? It is the copper loss, which we call it as variable loss, because the current I1 is varying with load, therefore it is a variable loss. Wi, as I saw, which depends on the magnitude of the voltage, is a constant loss. Therefore whenever I want to have a maximum efficiency, the losses, the variable loss should be equals to constant loss. If I load the transformer such that the current given or current drawn by the primary winding, okay, is given by this relationship I1 square R1 R equivalent 1 is equals to Wi, I will be getting the maximum efficiency for the transformer. So the condition for maximum efficiency is variable loss should be equal to constant losses, or copper loss should be equal to core loss in a transformer. I have one more topic to be covered in this, okay, session, but now let us do this in the next session, tomorrow's session, along with some problems for this topic. Now today we saw that different types of losses taking place in the transformer and their dependency on the parameters like voltage and current, okay, and the classification of losses in the transformer as core loss and copper loss, and we also done the expression for efficiency and the condition for maximum efficiency on the transformer. The today's session started with the derivation of EMF equation in a transformer, and next session I will be doing some problems on the transformer, okay, about the induced EMF equations and evaluation of efficiency or estimation of efficiency of the transformer given the losses and some other conditions on the transformers. Okay. Thank you.